Welcome to a deep dive into the Hartman Phononic Lattice gravity drive and Lenticular Aerospace vehicle. This revolutionary concept merges advanced physics, materials science, and aerospace engineering to create a craft capable of manipulating gravity and propelling itself without traditional fuel. In this video, we'll explore the foundational principles, subsystem architecture, materials, control logic, simulation protocols, and environmental adaptability that define the H-PLGD system. Let's begin by setting the stage for this journey into the future of propulsion technology. The heart of the H-PLGD is a mathematical and physical framework that enables gravity control through phonon-mediated mechanisms. The system leverages tunable crystal lattices, where the curvature of phonon bands, Polariton coupling, and plasma resonance are precisely controlled. This allows the craft to generate spatial gradients in inertia, effectively shaping how gravity acts on it. By manipulating these gradients, the vehicle achieves lift and thrust in ways conventional aerospace vehicles cannot. Phonons, the quantum vibrations within a crystal lattice, play a central role in the H-PLGD. The dispersion relation for these phonons determines how energy and momentum are distributed. By engineering the lattice so that certain regions have negative curvature, the system can create zones of negative effective mass. This is interpreted as negative gravity, a key mechanism for controlling the inertial environment inside and around the craft. The ability to actively tune the phononic lattice is what sets the H-PLGD apart. Control vectors adjust parameters like mass, stiffness, and lattice spacing in real time. This dynamic tuning produces spatial gradients in effective inertial density, allowing the craft to manipulate its own gravitational field. The result is a system that can generate lift, thrust, and even directional control by simply altering the internal structure of its materials. Another breakthrough in the H-PLGD is the use of Polariton coupling and vacuum pressure modulation. By controlling the interaction between phonons and photons, the system can shape the local vacuum mode density. This is achieved through Casimir pressure modulation, which produces net forces on the lattice. Such control over the quantum vacuum enables new forms of propulsion and field manipulation, further expanding the craft's capabilities. H-PLGD's longitudinal wave spine is a central structural feature that supports energy exchange between different modes within the craft. By coupling spine modes with hull phonons, the system enables precise thrust vectoring. This interaction is governed by a specialized Hamiltonian, allowing the craft to direct energy where it's needed most for maneuvering and stability. Drive propulsion, the H-PLGD injects energy into the system, exciting quasiparticles such as phonons and polaritons. These excitations populate negative mass bands, which are essential for generating thrust. By carefully managing energy injection and resonance conditions, the craft can sustain propulsion without the need for traditional fuel or reaction mass. Maintaining coherence across the entire craft is vital for stable operation. The H-PLGD uses phase-locked Polariton fields to ensure that all regions of the vehicle respond as a unified whole. This non-local coordination maintains the global inertial topology, preventing destructive interference and maximizing efficiency. H-PLGD is divided into several key zones, each with a specialized function. From the adaptive plasma envelope on the outer shell to the phononic mantle, Polariton interface, longitudinal spine, excitation core, and non-local coupler network, every region is meticulously engineered. This layered architecture supports the complex field interactions required for gravity control and propulsion. Lenticular craft features a disc-like shape with a domed upper and lower surface, providing symmetry and structural efficiency. The internal volume is partitioned into concentric zones, each optimized for a specific role. This geometry is not just aesthetic, it's fundamental to the craft's ability to manage fields and forces in 3 dimensions. Zone A forms a thin outer layer, housing discrete Helmholtz-like plasma cavities arranged in a ring. These resonators can be tuned for pressure control, drag reduction, and ionization in air or sea, or to provide an artificial plasma boundary in space. The interface between Zone A and the inner regions is crucial for both mechanical and electromagnetic coupling. Inside the plasma envelope lies Zone B, a thick shell composed of phononic crystal panels. Each panel is a tunable lattice, capable of generating negative curvature bands for gravity control. The mantle is vertically stratified, allowing for different inertial properties above and below the midplane, which is essential for lift and maneuvering. Zone C acts as a transition layer, featuring polar materials and thin cavities that enable strong phonon-photon coupling. This interface is responsible for converting mechanical information from the mantle into electromagnetic and vacuum mode modifications, playing a pivotal role in the craft's propulsion and field shaping. The core of the craft is the longitudinal wave spine, a structural column that supports acoustic and plasma waves. This spine defines the thrust axis and serves as a phase reference for the entire system. Radial branches extend from the spine, distributing energy to the mantle and interface layers for coordinated propulsion. Zone E is the energy injection hub, located around the spine's core. It contains active materials with engineered band structures and integrated electromagnetic drive sources. This engine seeds phonons, polaritons, and other quasiparticles into the system, providing the energy needed for propulsion and field control. Distributed throughout the craft, the Nonlocal Field Coupler network ensures phase coherence and synchronization across all zones. These hubs maximize Polariton lifetime and coherence length, binding the entire system into a single, responsive unit. This is essential for maintaining stability and executing complex maneuvers. To achieve precise control, the craft is segmented into azimuthal sectors, radial bands, and vertical layers. Each segment can be independently tuned for phononic, polaritonic, and plasma parameters. This segmentation allows for localized control of lift, thrust, and stabilization, enabling the craft to adapt to changing conditions and execute complex maneuvers. H-PLGD's performance relies on advanced materials engineered for specific roles. These include phononic crystals for gravity control, Polariton active layers for vacuum shaping, plasma-responsive materials for environmental coupling, and specialized core and coupler materials for wave and coherence management. Each material is chosen for its unique properties and ability to respond to control inputs. Phononic crystals form the backbone of the gravity control network. These materials are composed of high-stiffness ceramics, ultra-low-density aerogels, and gradient-density composites. Their unit cells can be dynamically tuned through piezoelectric, magnetostrictive, thermal, or electrostatic means, allowing for real-time control of effective mass and curvature. The Polariton interface relies on materials with strong phonon-photon coupling, high dielectric contrast, and low optical loss. Thin film manufacturing enables precise control over Polariton dispersion and Casimir active multilayers. By adjusting field bias and cavity spacing, the system can modulate vacuum pressure and enhance propulsion efficiency. Zone A's plasma envelope is constructed from high-temperature ceramics and conductive composites. These materials support tunable plasma density, which is controlled via RF injection, microwave pumping, and ionization lasers. The Helmholtz resonance of each cavity can be dynamically adjusted to match environmental conditions. Longitudinal wave spine and excitation engine require materials with high Q factors, strong coupling to the mantle, and excellent thermal stability. Plasma waveguides, phonon-acoustic rods, and hybrid conduits are used to transmit energy efficiently. The excitation core features doped quantum well structures and rare earth embedded lattices for multi-level energy transitions. Maintain global coherence. The Nonlocal Field Coupler uses materials with long Polariton lifetimes and high phase stability. Topological insulator films, 2D materials like graphene, and Polariton active met surfaces are among the candidates. These materials ensure that phase information is transmitted rapidly and reliably across the entire craft. H-PLGD's control system is organized into 3 layers: local field modulators, LFM, regional field coordinators, RFC, and the global field orchestrator, GFO. Each layer manages different aspects of field modulation, from local curvature and phase to global coherence and flight commands. This hierarchy ensures robust, real-time control over all subsystems. Each control zone receives a vector of inputs governing phononic, polaritonic, and plasma parameters. Feedback loops monitor curvature, phase, and resonance, adjusting control signals in real time. This closed-loop system allows the craft to respond dynamically to both internal and external changes, maintaining optimal performance. Control system defines a global field topology, combining phononic curvature gradients, Polariton phase maps, and plasma pressure zones. This topology determines the effective inertial density and the net force field acting on the craft. By shaping these fields, the H-PLGD achieves precise control over its motion and stability. H-PLGD supports multiple flight modes, including hover, thrust, maneuver, stabilization, and high-G operations. Each mode is executed by adjusting curvature gradients, phase maps, and plasma settings. The global field orchestrator selects and transitions between modes based on mission requirements and environmental conditions. Validate and optimize the H-PLGD. A comprehensive simulation framework is used. The craft is modeled in 3 dimensions, with high spatial and temporal resolution. Diagnostic observables such as phononic curvature, Polariton phase, plasma envelope frequency, and excitation energy are extracted from each zone, providing detailed insight into system behavior. The simulation grid covers the full geometry of the craft, using cylindrical coordinates for accuracy. High-resolution matrices track the evolution of fields and observables over time. This allows engineers to predict system responses, identify potential issues, and refine control strategies before real-world deployment. Key observables include phononic curvature, Polariton phase, plasma envelope frequency, and excitation energy. These metrics are monitored in real time, both in simulation and on the actual craft. Embedded sensors and diagnostic probes ensure that the system remains within safe and optimal operating parameters. Simulation evolves the field topology using coupled nonlinear equations. These equations govern the dynamics of phononic, polaritonic, and plasma fields, as well as their interactions. By integrating these equations over time, the simulation predicts how the craft will respond to various control inputs and environmental conditions. Each simulation run begins with initialization, setting control parameters and excitation profiles. The system then evolves over time, integrating field equations and extracting diagnostics. Results are validated by comparing simulated observables with experimental data, allowing for iterative refinement of both the model and the physical system. Simulation observables are mapped to physical diagnostics using embedded sensors. Phononic curvature is measured by sensor arrays, Polariton phase by interferometry, plasma resonance by spectrometers, and excitation energy by quasiparticle detectors. This mapping ensures that simulation results are grounded in real-world measurements. H-PLGD generates motion by creating spatial gradients in effective inertial density. By manipulating internal fields, the craft essentially falls toward regions of low inertia that it creates itself. This principle enables lift, thrust, and maneuvering without the need for air or reaction mass, setting the H-PLGD apart from all conventional vehicles. Lift is achieved by tuning the upper and lower layers of the phononic mantle to different curvature profiles. The lower layer is set to negative curvature, reducing inertia below the craft, while the upper layer maintains higher inertia. This creates a net upward force, allowing the craft to hover or ascend without traditional lift surfaces. Thrust is produced by activating the longitudinal wave spine, which injects directional phonon energy into the mantle. By creating a forward inertial slope, the craft is pulled in the desired direction. Thrust vectoring is achieved by selectively inverting curvature in specific azimuthal sectors, providing agile and precise movement. H-PLGD rotates by asymmetrically exciting different azimuthal sectors. Pitch is controlled by adjusting curvature in the front and rear sectors, roll by shifting left and right sectors, and yaw by introducing Polariton phase gradients. This allows the craft to rotate smoothly in all directions without mechanical control surfaces. Unlike conventional aircraft, the H-PLGD can translate sideways without rotating. By creating a horizontal inertial gradient, the craft slides along the desired direction. This unique capability is made possible by the precise control of internal fields and inertial densities. Stability is maintained by the Nonlocal Field Coupler, which synchronizes Polariton phase and dampens oscillations. If turbulence or external forces disrupt the field topology, the NFC restores symmetry by adjusting phase, curvature, and plasma envelope. This acts like a field-based gyroscope, ensuring smooth and stable flight. The H-PLGD supports various flight modes, including hover, cruise, maneuver, evasive, and high-G operations. Each mode is tailored to specific mission requirements, with the control system dynamically adjusting field parameters to optimize performance and safety. The H-PLGD is designed to operate in air, sea, and space. Each environment presents unique challenges, such as turbulence, density, and vacuum. The craft adapts by reconfiguring its plasma envelope, phononic lattice, and Polariton interface, ensuring optimal performance regardless of the medium. Plasma envelope is tuned for each environment by adjusting density, resonance frequency, and coupling coefficients. In air, it reduces drag and ionization. In sea, it suppresses cavitation. In space, it acts as an electromagnetic boundary. This adaptability is key to the craft's multimedium operation. The phononic crystal mantle adapts its unit cell parameters and curvature control to match environmental demands. In air, it maintains high curvature gradients for lift. In sea, it increases stiffness for damping. In space, it maximizes negative curvature for inertial shaping. This flexibility ensures efficient operation everywhere. Polariton interface adjusts its dispersion and Casimir pressure based on the surrounding medium. In air, coherence is moderate. In sea, it acts as an acoustic barrier. In space, coherence and vacuum shaping are maximized. This ensures that field interactions remain effective in all conditions. Transitions between air, sea, and space are managed by sensor-driven impedance detection and automatic reconfiguration of all key systems. The global field orchestrator ensures phase continuity and thermal compensation, allowing the craft to move seamlessly between radically different environments without manual intervention.